Probably the most common anthropogenic or man made contaminant in groundwater that impacts water supply wells is nitrates. And you can find that throughout the United States and throughout the world, actually. There's a number of sources. We'll explore that today. But it's really a pretty common contaminant out there. And we'll look at the geology, we'll look at how it occurs in wells and some of the remediation options to clean up nitrate or to at least treat it when it's in the wells. So that's what we're going to be talking about today. Hey, everybody, I'm Tom Ballard, the groundwater guy, and today we're going to be talking about nitrates in your water supply. We have the Water Masters program, and it covers this is basically kind of a peek into that program, our videos here. And these are kind of the areas that are covered in the Water Masters program. This kind of falls in the water supply management area when we're looking at contaminants. It's really how we deal with our water supply management, and so that's the category it falls into here when we're looking at nitrates. So let's dive in and bring up our slides here. Um, Let me get this going. All right, so we're going to talk about managing nitrates in drinking water. This is really kind of a comprehensive guide. We're going to look at everything from the sources to the treatment, and this is really based on a really good study that was done in 2012 and a subsequent update from the University of California, Davis. So we're pulling a lot of information from that because there really isn't anything out there like it. I mean, it's a multi-volume study and a lot of good information there. And so you can look that up online if you're really interested in diving into nitrates. It does focus mainly on California's Central Valley and some of the areas up near Northern California. But the principles and the geologic principles apply pretty much anywhere. So that's why we pulled that in. And like I say, there's really nothing else like it. So it's a very comprehensive study. And so that's why we mainly used it here. We pulled in some other sources, but that's the main study we used. So you'll see that reference throughout. So our executive summary here is basically nitrates is NO3, that's minus. We measure it as nitrate as N. Uh, that contamination is widespread in agricultural areas, affects many small systems. It's a shallow water contaminant, so generally shallow groundwater, you're going to find more nitrates. And we see it mainly in agricultural areas. The sources from agriculture, feedlots, fertilizer is the main source, but it can also come from things like septic systems and some of the water treatment plants and other things. So a wide range of sources. We can, if you want to really dive into the weeds, we can differentiate some of these things using isotope studies, where you can actually tell based on nitrogen oxygen deltas whether it came from a feedlot or fertilizer or septic system. So if you really want to dive into that, isotope studies are the way to go if you're really looking at identifying the source. And probably not necessary for most things because either it's there or not, and you're exceeding the water level, MCLs or not. But if you're doing a detailed source study, then that might be a way to go. So the core risks are acute methemoglobinemia for infants. That's a tough one to say. Basically, it's blue baby syndrome is probably the easier way to say it. So compliance is a tier one priority. The most cost-effective path is to prevent and minimize entry. So well integrity and source protection are really where you want to go. Treatment gets a little more complicated and expensive. So if you can avoid treatment, a lot of times this is in nitrate in your well is going to be a well seal issue. I can tell you that. We'll talk a little bit more about that as we get a little farther on. But the vast majority of cases I've seen where we got nitrate in wells, it's usually a poorly designed seal or a failed seal, and that's where you can start your look anyway. So we want to optimize our non-treatment and save on costs. So if we can do blending or alternative sources, that's going to be the way to go. We're going to talk more about that. And then we want to select the right treatment. So basically, what we're going to talk about today is sources and occurrence, the hydrogeology, well construction, any retrofits to fix any problems at the wells, blending, treatment, cost, compliance, and resources. So we're going to kind of look at the whole thing. So um, nitrate contaminant represents a public health concern and a regulatory compliance issue. There are MCLs, and early intervention and proper management strategies can significantly reduce the risks and costs. So if we know we have a well problem, we can go in and fix that well. And I have some experience doing that, and I know that approach works. You just have to do the proper diagnostics and go in and modify your well, and that can reduce your nitrate problem right there. So I'll talk a little bit more about that later on. All right, health impacts and regulatory framework. So the methemoglobinemia, the blue baby syndrome is a risk for infants less than 6 months. 6 months. Sensitive groups include pregnant individuals and those with enzyme deficiencies have particular sensitivities to nitrates. There's emerging evidence that associations at long-term exposures, even below the MCL, can have cancer and reproductive outcomes, but that is currently under study, so there's no conclusive evidence of that, but there is some information that points that direction. So you want to be cautious and not just say that it's going to affect babies because there could be some other factors there as well. So regulatory, the EPA MCL is nitrate at 10 milligrams per liter as nitrogen. So there's a couple ways to measure that, and we usually measure it nitrate as nitrogen, but there you can measure it as nitrate as well, and there's a little bit different MCL for that. Nitrite, which is a little bit different form, is 1 milligram per liter as nitrogen. So nitrate is N is 1 milligram per liter. Nitrate as N is 10 milligrams per liter. Key Tier 1 public notification required within 24 hours of nitrate MCL exceedance. So that's something you need to do, and you need to monitor for this. So, and you need to notify your customers if you do have MCL exceedances. So the citation there is 40 CFR Part 141. That's the National Primary Drinking Water Regulations. Different states may have different regulatory requirements or MCLs. So you can check, you probably need to check with your state and see what's applicable there. This is the federal levels from the EPA that we're talking about here. So all right, so sources of nitrate in groundwater. So what drives nitrate loading? How do non-point and point sources differ? And where are utilities most vulnerable? We have two different sources. We got point sources and non-point sources. So let's talk about those a little bit here. Non-point tends to be dominated by agricultural land uses. And this is mainly going to be fertilizer and manure applied over broad areas and leaching below the root zone. So that's going to be considered a non-point source. Point sources are going to be things like septic systems, wastewater treatment, percolation ponds, manure storage lagoons, animal corrals, feedlots, and facility spills. That may be fertilizer processing or mixing when we talk about spills. The pathways, infiltration through unsaturated zone. So it's generally going to start as a surface contaminant, shallow groundwater contaminant, and work its way deeper depending on your hydrogeological situation. Wellbore conduits, depending on your pumping situation, you can get some migration that way too. Um, so the impact scale, agricultural sources dominate the regional loading. Probably around 94% of nitrate contamination in groundwater is from agricultural sources. So point sources can create severe local hotspots. So you get into urban areas where there's less agriculture, and you can still get nitrate from these local hotspots. So understanding source type and proximity to wells helps prioritize protection strategies. Regional programs for agriculture, targeted actions for nearby point sources, and those types of things can really help you manage things. And we got a diagram here that really shows our sources here, and we get that, our agricultural sources, which are the non-point source, lawn fertilizer in residential areas, that would be considered non-point, and then your point sources, septic, wastewater treatment plants, lagoons, animal feedlots, those types of things. Um, you're going to get vertical migration through the soil. You're going to get it into the unsaturated zone. It's going to flow through preferential pathways. You're going to get it into the Bedos zone, and it's going to work its way into the groundwater. You're going to get lateral flow there, and then it's eventually going to, and we're going to talk about the processes there, work its way to drinking water wells. um, so back talking about the sources a little bit, is agricultural fertilizers is really the dominant contributor. Synthetic nitrogen fertilizer in cropland is really the largest regional source in intensive agricultural basins. And that's why the Central Valley of California was chosen for that study, because a lot of farmland there, a lot of agricultural fertilizer applications, and a lot of nitrate contamination as well. And so a lot of the aquifers in that part of California, in the Central Valley, are contaminated with nitrates to varying degrees. So excess nitrogen beyond crop uptake increase the risk of nitrogen leaching. Risk is elevated with over application and inefficient irrigation. So changing up irrigation practices is really the key to managing this, because the nitrate runs off. You got more fertilizer being applied and more nitrogen that can be used by the plants. And where's it going to go? It's going to go into groundwater. It's going to run off into the streams and lakes, but it's also going to go into groundwater. So practices that increase risk: fall applications before heavy rains, flood irrigation, and shallow groundwater are going to be increased risk factors. So best management practices really are applying the right rate, the source, the time, the place, looking at the weather and the time. Fertigation, which is really injection of fertilizers, so it's going to be real specific to the plant's needs in that area. So you're not doing a broad brush application, you're actually injecting right where it's needed. So that's going to limit the amount of excess nitrogen that can make its way to groundwater. Cover crops can use excess nitrogen, so planting cover crops in the off season, very important. And things like alfalfa can take up a lot of nitrogen. So those are and there's a lot of cover crops that will do that as well. And soil moisture and nitrogen testing. So this is really, you can see here in our diagram, it got shifted down a little bit here, but this is from data from the Tulare Basin and Salinas Valley case studies in 2012, part of that University of California Davis study. And you can see that cropland fertilizer, 76.4% of the agricultural applications, cropland manure, 17.3, and other sources, 6.3. So the fertilizer application and inefficient use of fertilizer is really the big culprit here, and that's what we got to look at managing to reduce the nitrates in groundwater. Animal agriculture, manure and corrals, key nitrate loading from agriculture, animal operations, manure applications to fields add significant nitrates. So the manure spreaders in days of old, they still do it, but now they do it a little more concentrated, so you can get more concentrated nitrogen. The timing and rate is critical to prevent leaching. So it needs to be planned out and not just done just massive spreading around. And I think we're seeing progress in those areas when we apply manure. Corrals and feedlots, direct infiltration from high density animal areas, especially on permeable soils. This is also a problem in the Central Valley of California. There's a lot of, usually in the Central Valley, there's a lot of feedlots down there, and you can just go by and you can see all the manure out there, and it's raining. The cows are stepping in, and it's working its way into the soil. So it makes for a mess, and it can create local hotspots here. Manure storage lagoons, seepage risk of unlined or poorly lined. Monitoring and lining is essential. So we don't want unlined manure storage lagoons anymore. Those I think are on their way out, but there's still some in existence, and those probably need to go away and be replaced by lined lagoons. Um, the relative loading, animal related sources contribute smaller regional shares in cropland, but can still create severe local hotspots near wells. So if you have wells that are near feedlots, you may start to see nitrate issues, or you may already have nitrate issues. You're certainly want to get a test for nitrate. So corrals contribute approximately 0.7% and lagoons 0.1% of regional nitrate loading. So not huge, but certainly significant enough if you're in those areas where they're located. And we can see kind of the flow chart here of uh, of how it works its way into groundwater. All right, urban residential sources, that's going to be septic and wastewater treatment plants. So septic systems, nitrogen in wastewater converts to nitrate and percolates. Risks increase with high system density or shallow water tables. So um, in some places, for instance, also in California, there's been studies done where they look at up in say Napa and Sonoma areas where they have a lot of wineries. They do leach fields for their wine waste, and they actually have to do nitrate loading studies to determine that they're not going to add excess nitrogen to groundwater. That's probably something that needs to be done. It's an impact study that needs to be done, and you need to make sure you got proper separation and proper design so you're not doing excess loading of nitrogen to the groundwater table, and especially important when you have shallow groundwater tables. So that those cumulative impact studies very important. We should really see those in other areas too. California uses those. I've started seeing them elsewhere as well, and that's going to really inform you in how you're going to design these leach fields and systems to minimize nitrate loading to groundwater. So wastewater treatment plant percolation basins can load nitrate where effluent is not fully denitrified prior to infiltration. Urban runoff and landscaping fertilizer, that's typically going to be pretty minor, but it may affect shallow wells locally. So it can still be a contributor, and probably rarely anymore. Backflow cross connection events can introduce nitrate into distribution without proper protection. So that's where having the backflow preventers and the cross connection control really comes into play. Is you don't want any backflow in your system that can contaminate parts of your distribution line. So um, so anyway, the urban sources generally are going to be smaller, but they can create regional hotspots. All right, case study, source contributors. This is in the California basins. So we can see that the estimated regional source contributions, this is going to be based on that UC Davis study of the Tulare Lake Basin and Salinas Valley. You can see cropland, 93.7%. So manure and fertilizer contributed almost 94% to regional nitrate loading. The others are pretty minor, so they can be significant if you're right next to a well, but they're almost insignificant compared to fertilizer and manure and the feedlot. So that's something we really need to or fertilizer application. The feedlots are farther down here. So um, and everything else relatively minor, less than 2%, all the way down to 0.1%. And you can see on our chart here that for the Salinas Valley and Tulare Lake Basin, which is in the Central Valley, you can see that 93.7%. So the vast majority. And I think that probably holds true in other parts of the country as well. You get into the Great Plains where you have a lot of croplands and stuff, and you're probably going to see relatively similar percentages where you have a lot of croplands and fertilizers going on. All right, so legacy contamination and time lag. Groundwater flow is slow, often only a few feet per year, so today's nitrate contamination may reflect land use practices from decades ago. And this is really true because we see in these studies in different parts of these basins that we're seeing nitrate showing up where it's removed from where it was probably applied. And we actually there's been some of these isotope studies I mentioned earlier. They're looking at the sources and you see the remove, but they've actually worked that way over time through slow groundwater flow, and now it's managed to uh, impact pretty much the entire basin. So the Vado zone um, acts as a long-term storage reservoir, continuously feeding nitrate into groundwater plumes. So it's a continuing source basically, and that basically gets recharged from over application of fertilizer too. So you're seeing it continually being recharged, and that's continually leaking and feeding nitrate into groundwater plumes. Management implications. Even with improved agricultural practices today, nitrate concentrations in wells may continue to rise before eventually stabilizing and declining. And we'll talk a little bit about how natural attenuation works and why you don't want to count on that too much. So here's kind of an illustrative time chart. Um, land applications 80s to 90s may reflect in well detections today. That it goes into Vado storage, it continues to leak out, and we may start seeing it in wells that are removed from the actual source area years and years later, decades later. All right, hydrogeology and geochemistry. So, why is nitrate highly mobile and persistent in many aquifers? Because it is. It's highly mobile, it does not attenuate well. And so, we're going to look at why that is, and we're going to look at the processes governing transport and attenuation. So, mobility, we're going to talk about advection and dispersion. Nitrate moves freely in groundwater. It's highly mobile. It's conservative, non-degrading, and weakly absorbing, which means it doesn't stick to aquifer materials. So, like some of these polar molecules will. So it really does not stick to the clay particles, and it just keeps moving at the rate of groundwater. So, bulk transport, advection, bulk transport with groundwater flow, the nitrate moves at the same rate as water itself through the aquifer, and dispersion. It'll spread and dilute itself in plumes over time, distance due to the heterogeneity of flow paths and velocity. So you'll see this dispersion effect, and that's illustrated in the chart to the right here. You can see over time as it moves, the concentrations will get lower, but they'll spread out over bigger areas. But the mass the mass balance actually stays pretty close to the same because it really doesn't degrade very well, especially in oxic areas with higher oxygen or shallow aquifers where it's mainly showing up. And so you'll get the dispersion, but you won't get a reduction in mass. So it contributes to mass, and we'll see nitrate levels actually going up over time, even though you get this dispersion going on. So preferential pathways, coarse sediments, fractures, annulus can accelerate transport and create irregular plumes. I've worked on some wells where we actually had some fracture zones in the wells that were actually connected to some manure storage areas, and it was actually creating nitrate levels in the well above MCL. So, and the fracture was actually tapping into this manure storage area that was a fair distance away from the well, but we basically had to go into the well and we had to modify that well and seal off that particular set of fractures, and we were able to reduce the nitrate concentration in the well. So it will move through these fracture zones, and we have seen that. So that is an important consideration. All right, attenuation, denitrification limits. So denitrification, which is the process of reducing nitrates to nitrogen gas in groundwater and soil, requires anoxic conditions and electron donors, so organic carbon and reduced minerals like pyrite to convert the nitrate to nitrogen gas. So anoxic conditions are reducing conditions or low oxygen conditions. So basically, that's what shallow water is not. Many alluvial aquifers used for supply are oxic or aerobic, so they have high oxygen, and that limits the natural denitrification and allows the nitrates to persist for decades. And that's why you get the dispersion. It'll reduce the overall concentrations, but not the mass, because the conditions aren't right for denitrification to occur. Um, the redox stratification, deeper, older waters can be more reducing, so site-specific evaluations may be needed to identify potential natural attenuation zones deeper. So if you have wells in an area, or you're planning on putting wells in areas where there's no nitrate, you may want to look at deeper wells and sealing off some of those lower zones that are more oxic, where the nitrate is concentrated, and look at deeper zones that are a little more reducing, where you get the denitrification and lower nitrate levels. So um, denitrification is a primary natural process that removes nitrate from groundwater, but conditions are rarely optimal throughout an aquifer for denitrification to happen, and thus we get the buildup. So, and if we're actively applying fertilizer, excess fertilizer, we're getting more nitrogen coming in than can be denitrified, and thus you have a problem that's compounding over time. So just an operational note here, do not rely on natural attenuation for compliance without strong evidence. You're going to want to sample for dissolved oxygen, ORP, and electron donors before you assume any natural removal capacity or denitrification going on. You're going to need to prove that you have denitrification going on before you can really rely on that. So that's important. Groundwater vulnerability and capture zones. Shallow water tables increase vulnerability. There's a shorter travel time for contaminants to reach the groundwater. And also, they tend to be more aerobic or oxic, like we talked about. So, you're not going to get denitrification going on. So, permeable soils and aquifer materials can accelerate nitrate transport. Clay layers can provide protection, and that's usually going to be vertical protection from downward migration of nitrates. Um, because nitrate does not sorb to the clays, it's going to, so you're not going to get a lot of nitrates sorbing to the clays, but it's going to provide inter-aquifer protection. So basically acting as an aquitard and keeping the nitrates from migrating into lower zones. So, however, multiple aquifer wells can short circuit contamination, allowing nitrate to migrate to deeper zones. Really important if you screen across multiple aquifers that you understand what you're doing, you do the proper testing, and you understand the dynamics of the flow situation, any contaminants, and how you can cross contaminate aquifers this way, because it can happen, and you don't want to be the culprit there that's going to get sued for contaminating formerly clean aquifers. So you want to understand the well capture zones, the subsurface area providing protection to the well. That's critical for source protection planning. So delineate well capture zones prior to land use management and monitoring efforts. Target source control in areas that directly impact your supply wells. So you're going to want to understand where the capture zones are, and you're going to want to do you're going to do the source area protection around those areas where the capture zone of your well is located, so you understand what's coming into the well. Now, obviously, nitrates can migrate in through the plume transport, but if you have feedlots, if you have any of those point sources nearby in your wells, you need to understand where your capture zone is in your well and how you might be impacted from that. All right, well construction and integrity, uh, critical components for protecting water quality, the components of your well, the casing, screen, sanitary wellhead, and continuous annular seal blocking vertical leakage. Sealing materials need cement, sand, cement, grout, high solids, bentonite per the standards. Um, Public water supply wells commonly require a 50-foot annular seal, but you want to verify state and local standards. And I would say don't rely on that 50-foot seal. The seals need to be based on the geology, and a seal needs to seal off that upper aquifer that might be impacted by nitrates. So if that's a 100-foot seal, it needs to be a 100-foot seal. You want that grounded in a clay or an impermeable zone, so you're not going to get any downward migration into your well. So that well seal needs to be based on the geology and the hydrogeology to be effective, and not just blindly put in a 50-foot seal because that's what your state regulations say. And like I say, the vast majority of nitrate contamination in wells is caused by an improperly installed or a failed seal. And I see it time and time again. It's the first place I look when somebody calls me about a nitrate problem in a well. The first thing I ask for is their well driller logs, and I look at that, and a lot of times that's going to tell you right there what the problem is. So you're going to want to construct a well based on geology and hydrogeology, not based on the standard. Those are just recommended minimums, and you don't want to do that without thought to the geology, because you may end up with a useless well or a contaminated well, and you spend all that money. So why not do it right and get the seal right? So if it means hiring a geologist to come in and look at it, well, so be it. I always like to say geologists are cheap, so hire two. But the important thing is you want to understand the geology as you build your well, and build the well to reflect the geology, to minimize the potential for contamination in the well. So you want to avoid long multi-aquifer screened intervals. You want to set your pump intake to target the best quality zone, and make sure you're not dragging any of that contamination around. So a properly constructed well with an adequate annulus seal is the first line of defense against nitrate contamination from surface and shallow sources. So I can't overemphasize that enough. That's the issue right there in a lot of cases, and you can avoid having to treat for nitrates or doing anything more than just having a properly constructed well. Well modification and protection. There are retrofits, and I talked about this earlier. Installing an internal liner or inflatable packers to isolate shallow high nitrate zones along screen wells is one way to do it. You can also seal off those zones. You can adjust the pump intake to draw from deeper, lower nitrate zones when stratification exists. Um, you can consider VFDs to manage drawdown and optimize water quality zones. I'm a big fan of, if you know where, doing the vertical profiling in the well, understanding where your nitrates are, and sealing off those zones if you can do it without creating a lot of problems with your supply. You need to do a mass balance and figure that part out. You know how much you're going to reduce production in the well by eliminating the source of the nitrates, but it's well worth the effort. And then you can seal off that zone and probably reduce your nitrates down below the MCL. Well modification is often more economical than drilling new wells or implementing, and certainly cheaper than implementing treatment systems. That's the last thing you want to do, is a treatment system. So don't just assume that. You want to look at your source and see if you can manage that first. So install backflow prevention check valves and chemical feed lines and irrigation intertrees to prevent cross contamination. So we'll see a lot of water systems they supply water drip for drip irrigation system, and a lot of times there's tanks there that drip in the fertilizer. All well and good, but make sure you have proper backflow prevention and check valves to make sure none of that nitrate leaks back into your system. So locate and properly abandon nearby unused wells that can serve as conduits for source contamination. You don't want any open conduits to groundwater. So unused wells should be properly abandoned. And you want to maintain a sanitary wellhead, proper pad slope, pitless adapter, vermin-proof cap, and everything to prevent direct contamination. So you want to make sure that well is properly protected. All right, so non-treatment options. This is what you want to pursue first. Source management. Blending is certainly a viable option. We've talked about it in some of the other uh, shows I've done on different types of contamination, and blending is certainly a legitimate way to, if the way to go. If you have a low nitrate source and a higher nitrate source, you can blend from the different sources and make sure you're reducing down below the MCL. And you really don't need to do any treatment other than that. There's going to be a little bit more monitoring that's going to be required to confirm that you're hitting your targets because of the blending, but that's certainly a legitimate option and far cheaper than installing a treatment system, as we'll see shortly. And a new deeper well, if you don't have any options to deal with your existing wells, then you might want to look at a new deeper well and do some testing, a pilot hole, and do some vertical profiling to see if a deeper zone might provide you the nitrate free or reduced nitrate concentrations you need. So those are the best options for non-treatment. Um, Life cycle cost analysis, I'm a big proponent of this. You always want to look at comparing the capital and operating costs of non-treatment options against the long-term costs of treatment technologies, including waste management and monitoring expenses. Pretty much all the time, that life cycle cost will come out in favor of either a new well or blending or something like that. And generally, the treatment is going to be on the losing end of that analysis, just because you not only look at the capital expenditures of putting in a treatment plant, but you're also looking at maintaining, training, and all the soft costs that go into that. It's always generally going to be the higher cost alternative when you're looking at the total life cycle cost, which I recommend is the proper way to look at things, not just the low cost up front, but the life cycle cost for that particular process. System strategies, alternative sources, connect to neighboring system, regionalize to stabilize supply quality. So interconnections can help reduce your nitrate concentrations. Operational strategies, seasonal scheduling, source rotation, peak demand management with low nitrate sources. Sometimes we'll see seasonal concentrations rise or fall with the seasons. And so you need to understand if you're doing blending to make sure that you're taking that into account so you maintain the proper blend ratios. So treatment technologies and costs. Here are some of the treatment technologies we look at. And like I say, this should be your last option. You should really look at non-treatment. But if there's no way to avoid it, here's your options, and they generally are going to be some on some of the higher end ion exchange, reverse osmosis, biological denitrification, and electrodialysis. So those are the main ones. Your unit costs per thousand gallons. Generally, ion exchange is going to be the cheapest, but you can see the cost creep up there. RO is probably going to be the highest. Um, and biological denitrification, still a little bit. The jury is still out on that as far as I, uh, I feel it's, as you can see where it says under operational complexity, it's high because it requires a lot of hands-on management. Yeah, it can be cheaper, but you got to constantly be adjusting things, and because you're using bioprocesses that need to be adjusted to do the denitrification, and it just you really have to be monitoring it very closely. Um, so that makes the complexities high. RO is the same thing, and ion exchange and electrodialysis are more moderate complexity. So I would say probably IX is probably your best bet, but RO generally has a little bit more flexibility, and you can go to POU, POE systems, and not just a big central plant. So that can provide you some options there. So um, selection factors for small systems. We can see the best application for ion exchange, low to moderate nitrate levels, and areas with brine disposal options because you are going to generate brines. So there's going to be that limitation. Reverse osmosis, same thing. The best application is where you have multiple contamination issues beyond nitrates because RO will deal with it all. It tends to be energy intensive, high capital costs, and high operator skill requirements. Biological denitrification can work for higher nitrate levels and locations with strict waste disposal regulations because you don't need to deal with the brines. But the complexity that I talked about and the tweaking of the system that is constantly needs to be going on really makes it challenging. And there's bacterial regrowth concerns that get into the actual producing the bacteria and keeping that process going. So um, the point of use, point of entry systems, very small systems, those are generally going to be um, from the water system. A real small water system can go to the individual residences and install these units and deal with it. And those are generally going to be some type of RO or IX system that's going to be a small system at the individual residence. So those are your treatment options. I personally tend to think if you can deal with the source and or do some blending, you're a lot better off dealing with nitrates. So blending strategies, design and compliance. So the design, you're going to have online analyzers and SCADA control. Um, you're going to run these analyzers through your SCADA system so you can always monitor those. I recommend these days SCADA systems that have cloud storage and are accessible through the cloud so you can constantly monitor this. If you're doing blending, you may need to make some adjustments. So a SCADA system that's accessible over the internet and has cloud storage capabilities is really the way to go and has the inputs. A lot of modern SCADA systems, they've really come down in price. They take more inputs than they used to. And I'm a big fan of running everything or what you can through your SCADA system so you can do that monitoring in real time. And, especially if you have something sensitive where if you exceed your MCL, now you're going to have potential problems. So you're going to want to be able to monitor that, set alarms, and all that. So basically, the way it works is you're going to have your high nitrate source and your low nitrate source. Your target is the 10 milligrams per liter of nitrate as N. So you're going to do a blending manifold. You're going to have your nitrate analyzer that's going to report in real time through your SCADA system so you can monitor that. And so basically the water that should be coming out should be adjusted so you have enough inflow from the low nitrate source that it's going to dilute the high nitrate source to get it down below the 10 milligrams per liter. So um, you're going to want to plan for seasonal variations. So you're going to want to monitor that. That's really important with blending or changes in well production. There's a number of factors that could affect the blending, so you're going to want to monitor that. So it's going to require a little bit of hands-on monitoring and maybe some seasonal tweaking, but it's still going to be a lot lower cost option than the treatment options we looked at earlier. So a real-time nitrate monitoring and control system is essential for blending operations. Without it, consistent compliance is difficult to maintain as source water quality can fluctuate. And I can tell you nitrate can definitely fluctuate because of the advection and dispersion we looked at earlier. So you can see concentration of nitrates coming into the well. It can be relatively high, they can drop. And so those concentrations are going to change. So that's why you need to be able to monitor this. And the regulatory agencies are going to make you monitor that on a regular basis as well. All right, cost considerations and funding. So we want to look at the total cost of ownership. So you not only want to look at the CapEx or capital expenditures, but you're going to want to look at the OpEx, which is your operating expenditures, such as the O&M, your chemicals, energy, your labor, your waste management, your monitoring, your placement cycles. So there's going to be OpEx and there's going to be CapEx costs that are going to be involved that you need to take into account. That's going to need to be worked into your asset management plan and your capital improvement plan to make sure you have the proper funding to to do what you need to do here. Small system economies, there's going to be some scale penalties. So smaller systems may pay a little bit more because they're going with a smaller system. So sometimes these systems are a little, if you look at it per 1,000 gallons, a larger system may be cheaper per 1,000 gallons than a smaller system, just because of the economies of scale. So there is funding out there available. The state revolving fund, of course, USDA, rural development, of course, local bonds can be available. So you're going to want to check into that. There are some private financing sources to provide bridge funding, and there are also leasing options as well. So a little you can get a little innovative on some of this financing too. So planning, alternatives analysis, pilot testing, value engineering, include residuals management costs. You're going to want to look at all that. And the proper way to look at it, as I said earlier, is going to be your life cycle cost. So you're going to want to look at the cost of this process over its lifespan and not just how much it costs you upfront. So, because it's going to come around and bite you if you only look at that upfront cost. So monitoring and compliance essentials, you're going to want to monitor your monitoring frequency is going to need to maintain that federal baseline. So the groundwater is going to be annually. Surface water is going to be quarterly. You're going to increase frequency of detections near the MCL, or you're showing any variability. You're going to have to, and if you're doing blending, you're probably going to have a more rigorous sampling schedule as well. You're going to want to sample all active source, collect from entry points to distribution system after treatment. You're going to want to report the sample results, corrective actions, and include nitrate information in your annual consumer confidence reports that go out to your consumers. So, state primacy requirements may be more stringent than the 40 CFR Part 141, so you need to check that. Don't just rely on the federal EPA requirements. You're going to want to check your state agencies. Public notification records, Tier 1 public notification within 24 hours for nitrate MCL exceedances. Follow the primacy agency templates and distribution requirements for these Tier 1 public notifications. But that's going to be important because you can be fined if you don't meet these deadlines. You're going to want to maintain your records, and that's always important for everything. We really want to see most water utilities go to a data-driven decision-making type of mode. And so keeping these records, digitizing them, tracking the trends, going to be very important to managing. It's going to make it management a whole lot easier. So you're going to want to go that direction eventually. And I think this is a good reason to do it here. So tracking trends, very important. You can get a snapshot of your system, but that's just a snapshot. If you want to look at the trends, that's going to give you some idea of what your long-term variability, seasonal variability, and other factors that can help you plan accordingly rather than just grabbing a sample and using that as your baseline and not looking at the trends. Records retention, minimum 10 years for chemical analyses, 3 to 12 years for other operational records. That's going to vary by state. If you digitize these things, you should really keep them up pretty much forever. And so you can go back. It's amazing how often you need to go back and look at some of these records. So I would say digitize them. Even your past records, have a plan to digitize these things and keep them around in digital format. They take up a lot less room than a hard drive takes up a lot less room than a filing cabinet for sure. So response planning, you want to develop and maintain an emergency response plan specifically for nitrate exceedances, including alternate water supply provisions for sensitive populations. So you're going to, if you have nitrate issues, you're going to want to have that emergency response plan that, obviously you're going to need to do the Tier 1 public notifications, but then that emergency response plan is going to have to kick in and deal with the situation to get things back on track. Best practices and recommendations, source water protection. You're going to want to engage the local growers, promote nutrient BMPs. We talked about that earlier. So best management practices so you're not contributing excess nitrate to the aquifers, identify and protect well capture zones, and participate in watershed planning. Working with the growers and the water suppliers together can really help manage those nitrate concentrations in the basin. Well asset management, implement routine inspections, conduct video logging as needed, perform proactive seal repairs, and you can actually monitor that. There's tools to actually sonic tools where you can go in and monitor the integrity of your seal. You're probably going to want to do that if your well has any significant age on it, just to maintain or to monitor the integrity of the seal. So you're going to want to monitor the casing for integrity issues. That's where your video logging is going to come in, because you're going to be able to monitor that casing. Water quality, establishing trends for nitrates with correlated parameters. So you're going to want to look at not only nitrate, but how it correlates with dissolved oxygen, oxidation reduction potential, sulfates, chlorides, conductivity, and other things that can affect nitrate concentrations and the denitrification process. And you're going to want to monitor the seasonal patterns. So trends are what are important. Operator readiness, you're going to want to develop SOPs, standard operating procedures for blending and treatment upsets, maintain spare parts inventory and vendor support, and implement proper staff training and emergency response. We talked about that. Prepare pre-drafted Tier 1 public notification materials so you're good to go on that if you need to, and establish alternate water supply logistics for sensitive populations just in case you start to exceed some of those parameters. Proactive nitrate management, much more cost effective than emergency response. So you want to have a comprehensive approach. All right, resources and key takeaways. Here's some resources for you. The US EPA, American Water Works Association, National Rural Water Association, state primacy agencies. Sometimes your state rural water association will have resources available as well, and they will always have um, RCAP is another resource. You'll have circuit riders out there that might be available from the rural water associations that can help you find the correct solutions. So a lot of resources are available, and you want to partake of those. If you have challenges, you don't have to go on your own. You can even talk to and form alliances with other water systems in the area. They may be experiencing some of the same issues, and you can trade technical know-how and solutions. That's a good way to do it. Talk with your neighbors. So key takeaways here: agriculture is the dominant regional nitrate source. Local point sources can create hotspots, but if you're in a big agricultural area where they're doing fertilizer, you're probably going to have a nitrate issue, and you need to deal with that. You want to prioritize well integrity and non-treatment options. That's going to be your low-cost option right there. Select treatment only when necessary and sustainable. It has to be financially sustainable. Uh, Maintain rigorous monitoring, documentation, and communication to ensure compliance and protect public health. You're going to want to have your stakeholders and your community informed, and you're going to want to engage with them and plan for watershed level solutions to nitrate contamination. Work with the farmers to see if we can reduce the nitrates that are going into the ground through some of these BMPs we talked about earlier. So in the long run, we want to have sustainable management of the aquifer and the agricultural resource as well. So by working together, hopefully you can sustain that. All right. So that is let me go back to our closing slide here. So that's our discussion on nitrates. Hopefully you got something out of it. If you did, please like, comment, share on the video. That helps with the YouTube algorithm. I respond to comments, but at least like it if you saw it, because that helps me get seen out there, and that's what we're trying to do, get more subscribers here. Um, my email address is below here. If you have any questions, please feel to reach out. I answer all the comments on the videos, and I also answer my emails. So I'm happy to talk to you. And until the next video, um, happy happy working in the water business, and you know, dealing with all these situations. We got a lot of them, and we're going to talk about a lot of them in coming shows.